In this paper, we propose a new method to compute compatible triangulations of two polygons, which allows us to create smooth transformations between two different shapes. Our method works in 3 stages. In the first stage, we calculate the valid vertex pairs. We call a vertex pair of a polygon valid if vertex UI is visible from uj and at least one of the two vertices is a concave vertex. For example, 2 and 5 is a valid vertex pair of the source polygon. We start from the concave vertices, for example, vertex V2 of the source polygon. We then find all the valid vertex pairs for vertex V2. And the valid vertex pairs for vertex V5. Similarly, we find the valid vertex pairs for the target polygon. We collect all the common valid vertex pairs of the source and target polygons, among which we select the one that can maximize the minimum interior angle. Now we triangulate each sub-polygon of the source polygon using D2AT triangulation. In the second stage, we map the triangulations back to the corresponding polygon using linear transformation. In the third stage, we refine the initial compatible mesh created in the previous phase such that we can increase the proportion of regular triangles and make the mesh more uniform. Here, we show examples of applying our method to compute compatible triangulations. With the compatible meshes created by our method, we apply the rigid shape morphing method to transform one shape to another. Our method introduces a very small number of Steiner points while the quality has been improved significantly. This benefits smooth transitions of shape morphing. Here, we compare our method with existing compatible triangulation algorithms. Here is one example of comparing different compatible triangulation methods. We can see that Surazhsky-Gotsman's method generates some long thin triangles that may cause inconsistent rotation problem for rigid shape interpolation method. The mesh quality of Baxter et al. Has been improved compared with previous methods, but the long thin triangles still need to be improved. Compared with previous methods, Leung et al. Has greatly improved the mesh quality, however, they may introduce a little more Steiner points. Our method generates tessellations similar to Baxter et al., but with a significantly simpler algorithm and improvements in mesh quality. Here is one more example of comparing different compatible triangulation methods. We can see that our method generates less number of Steiner points than the other methods, however, we achieve better mesh quality compared with the others. Here, we apply the compatible mesh generated by different methods to texture mapping. Our inputs are the source polygon with texture and the target polygon without texture. We then compute the compatible triangulations to build a bijection between the two polygons. With the compatible mesh, we map the texture of the source shape onto the target shape. This is the mapping result of using Leung et al.'s method. We can see some artifacts around the back of the alligator. This is the mapping result of using Baxter et al.'s method. We can observe some undesired distortion for both the tail and the back of the alligator. This is the mapping result of using Surazhsky and Gotsman's method. we can see some serious distortion around the abdomen of the alligator. Here, we apply the rigid shape morphing method to generate the transformations with texture. Here, we create animations with our compatible meshes using rigid shape interpolation method. Our method can be used by the industry to generate character animation. The artist can simplify their work by only drawing keyframes, and our system can be applied to automatically morph the keyframes.